So we've been looking at cell potential, standard cell potential. In previous chapters, we studied standard free energy change and the equilibrium constant. These three quantities are related to each other. So for a spontaneous redox reaction, the free energy change will be negative. The cell potential, standard cell potential, will be positive, and the equilibrium constant will be greater than 1. For a non-spontaneous redox reaction, the opposite is true. Delta G is positive, the cell potential is negative, and K is less than 1. Over here I said less than 1, didn't I? That's greater than 1. And so these are related sort of in a triangle, and we are going to discover the equations that relate them to each other. So potential difference, which is E, is the potential energy difference per unit charge. That's the maximum work that a reaction can do. So here we have potential difference is the potential, we get the potential energy difference in joules divided by the charge in coulombs. This is the work that can be done, and this is the charge in Q. So E equals maximum work divided by Q. So we could say that the maximum work done by the system, that can be done by the system, is negative Q E cell. So this negative comes about because the convention that's being used is that when work is done by a system on the surroundings, that's negative. Okay, so this negative just tells us the direction of the work, who's doing the work. So the system's doing the work, so this is negative. And this just comes from rearranging this equation. Any questions? So the charge that flows, and yes, I know charge was heat in Chem 1A. Just deal with it as charge now. There's only so many letters. So the charge that flows is quantified using Faraday's constant. So Faraday's constant is abbreviated with a capital F, and this is the charge in coulombs of 1 mole of electrons. So 1 mole of electrons has a charge of 96,485 coulombs. So the total charge, then, is Q, the moles of electrons from the balanced chemical equation. I'm sorry. What am I even saying? The total charge is Q, which is N times F. N is the moles of electrons times the Faraday constant. This is coulombs per mole. You multiply by moles of electrons, you get charge, Q. So we can substitute that into the equation we looked at relating the work. Work was negative Q times the standard cell potential. So we're going to substitute NF for the Q. We know that the standard free energy for a chemical reaction is the maximum amount of work that can be done by the reaction. So that leads us to this relationship. The standard free energy change is equal to negative NFE. N is the moles of electrons transferred in the balanced chemical equation. F is the Faraday constant. And E naught is the standard cell potential. So that's a very useful equation. Any questions? I'm not going to make you derive any of these, so. So use tabulated electrode potentials to calculate the standard free energy change for this reaction. Is the reaction spontaneous? Why does it say see next slide? I think it says see next slide because that used to be on the next slide, but now I put it on this slide and I didn't change it. So we just learned that delta G is equal to negative NF E cell. So there's two things we need. We need the standard cell potential, and we need the number of electrons being transferred. So this redox reaction has two half reactions. One of them is going to be sodium. Two sodiums going to sodium plus. And that must have two electrons over here because sodium's being oxidized, oxidation is loss of electrons. Or I can tell that I need to add negatives here to make the charge equal on both sides. So that's one half reaction. And the other half reaction is the rest of the pieces in there. 2H2O liquid going to H2 gas plus 2 hydroxide. Where do the electrons go in this one? On the left side. It's also going to be 2. It's going to be 2 for both of them because we're taking apart a balanced redox reaction. So when they balanced it, they fixed all that up. That's why these guys have 2s. So we need to find the standard cell potential. So here we have the reduction half reactions, right? The reduction half reaction would be this one. So H2O going to H2 plus 2 hydroxide. So that's this guy right there. And what I'm going to do is I'm going to find E for each of these half reactions and add them together. But one of them is going to be backwards. Because these are all for the reduction. We have one reduction, one oxidation. This one is written in the same direction as the one in the table, and so we leave the sign alone. So that's negative 0.83. So we've got negative 0.83 volts. And then we need to find the other one. The other one's going to be backwards, so we're looking for Na plus. And that's down here. So I'm using the equation backwards, so I'm going to change the sign on the potential. And there the potential was negative 2.71, so now it's positive 2.71 volts. Do I need to multiply that by 2? No, you do not multiply cell potentials by coefficients. So negative 0.83 plus 2.71. 1.88 volts, and that is equal to the standard cell potential. What is N for this reaction? It's 2. 2 electrons, 2 electrons. When we look at the balanced redox reaction, the electrons aren't shown. So you have to kind of go in and dig for them. But you can always find out. So N equals 2. And then what was F? That's one of those numbers that sometimes I remember and sometimes I don't. So we have N, F, and E. We can plug them in. So there's negative. We have 2 moles of electrons. And we have there's that, and 96,485 coulombs per mole of electrons. And then we multiply that by our cell potential, which is 1.88 volts. So I'm getting negative 3.63 times 10 to the 5. And my moles of electrons canceled out. So my units left here are coulombs times volt. And a volt is a joule per coulomb, so that ends up being joules.
It's volt per
I believe a volt is a joule per coulomb. So a joule per coulomb times a coulomb is a joule. It sounds like you're talking nonsense. So, is the reaction spontaneous? Yes, it is. Because delta G is negative. Yes?
Is the N always the number of electrons that are...
Yes. The N is the number of electrons transferred in the balanced chemical equation for the redox reaction. This is dumb because I don't have example 20.6. Skip that. So let's look at the relationship between standard cell potential and the equilibrium constant. So we learned that the standard free energy change was equal to negative RT times the natural log of the equilibrium constant. And we just learned that the standard free energy change is equal to negative NF times the standard cell potential. So these two things then must be equal to each other, right? So here we've got one is equal to the other. And so we can cancel those out. And we're trying to get the cell potential by itself. So we're going to divide by N and F. We're going to end up with RT over NF times the natural log of the equilibrium constant. So most of these types of calculations occur at room temperature, and so we can treat the temperature as constant, R is a constant, F is a constant. So instead of multiplying and dividing by these same numbers over and over again, we're going to lump them all together. So R is 8.314 joules per mole Kelvin. Temperature, 298.15 Kelvin, that's standard temperature. then we've got the Faraday constant. And then, just because we're going to convert the natural log to base 10 log, because electrochemists prefer base 10 logs. Yeah. So we end up with this equation, which is only valid at room temperature. So the standard cell potential is equal to 0.0592 volts divided by the number of electrons involved in the balanced equation times the base 10 log of the equilibrium constant. Any questions?
Can this equation change at all? What's the standard? So I would assume, like, if the temperature were to fluctuate or the equilibrium constant were to fluctuate?
If you wanted to mess around with the temperature, you'd probably go back to this. But then you're, calculating standard cell potential. It's not really standard anymore.
Yeah, I was just thinking of the
Yeah.
last chapter, sometimes it got changed.
We are going to see something where instead of the equilibrium constant, we use Q.
Oh, okay.
Yeah, which is a very useful thing. Any other questions? So use tabulated electrode potential, see slide 62, to calculate K for the oxidation of iron by H+. Oh, I hate it when I do this to myself on the slides. I used to be able to write on a slide and flip back, find something, and come back and continue writing on the slide, but that doesn't really work very well anymore, so I don't want to risk it. Okay, so we need to identify, our half reactions to get the standard cell potential, but then also let's remind ourselves of what the equation is. Standard cell potential, 0.0592 volts over N. Now, base 10 log of K. So standard cell potential, 0.0592 volts over N, base 10 log of K. And so we can solve for K if we know what the cell potential is. So our half reactions, I'm just going to write them down here. We've got 2 iron going to 2 iron 3. That's a 3. And how many electrons would that be losing? 6. And then the other half reaction must be hydrogen ions forming hydrogen gas. So 6 hydrogen ions forming 3 moles of H2 gas. And this is also going to have 6 electrons. So now we know that N is equal to 6. So we need to find the cell potentials. So Fe3 plus to iron solid. This is the one that's written backwards. It's the oxidation instead of the reduction, so I'm going to change the sign. In the reduction table, it says negative 0.036. So it was negative 0.36. We're writing it as an oxidation, so we change the sign. And then we find the hydrogen, and that is the equation for the standard hydrogen electrode, which is defined as 0. So what is our standard cell potential?
0.0%.
It'll be this guy plus 0. Excuse me, plus 0. So 0.036 volts is equal to 0.0592 volts over 6 times the log of K. So the log of K is 0.036 divided by 0.0592 times 6. 3.6486. Then how do I solve for K? I want 10 to the power, which is the anti-log. Four, 452, and there's a bunch of stuff after decimal point. That's plenty of sig figs. What are the units on that? No units. Good job. No units on K. What do you think? Is this reaction spontaneous?
Yes.
Yeah. K is larger than 1, and the standard cell potential for the whole thing is positive. So now we have the relationships between these three things. And this is one of those slides that, it's kind of nice that is pull it up on your phone, take a screenshot of it, and save it, because it's like got 3 good equations all right there. So a redox reaction has an equilibrium constant of K equals 1.2 times 10 to the third. Which statement is true regarding standard free energy change for the cell and standard cell potential for the reaction? Well, what do we observe about K? K is greater than 1. So this is going to be a spontaneous reaction, which means E cell has to be positive and delta G has to be negative. So that's going to be C. Any questions?